our next speaker is Wei Xie talking about dark photons. Let's welcome him.
Maybe. This one. Great. Thanks for the invitation. And this was my first time to Taiwan, so far I enjoyed. And I'm going to talk about the dark photon, followed by the keynote talk of action. Right now it's from spin 0 to spin 1. So I will tell you what's dark photon. This is one sentence. This is just similar as photon, but it has a mass and a small particle. And there is a worldwide effort to search for them. And because dark photon is so simple, and because it's a building block for the hidden sector, and after you possibly discover that you can generalize to the model you like. I will take you a small journey from Kaleidus and to cosmology. For Kaleidus, I'm thinking about like GeV or MEV dark photon, they can cascade decay. For the cosmology, I'm talking about dark photon as dark matter, and as light as 10 to the minus 20 or 10 to the minus 22 eV. So here's the plan, just tell you things in more detail. And the first part of the talk, I'm talking about the Kaleidus search, focus on how LC, like LCB search for the dark photon. And this dark photon will cascade decay to dimuon dielectrons. So then we'll go generalize the dark photon scenario to more like something photon phobic or the U1B minus L case. How do we project the dark photon limit to the model you like? The second part talk, I'm talking about different scale, like cosmology scale, galaxy scale, and also stars. So here, as I said, the dark photon is dark matter. So for the production, I'm talking about in the early universe or cosmology scale, we're talking about dark photon, how do they produce it, and then go to smaller scale, and like galaxy, I will review some short review on the small structural issues, and finally, I will show some preliminary result on how do we detect it in the Earth or from the Sun. Okay, let's get started. The weakly interacting massive particle. We have so the left-hand side is our beloved Standard model. In the middle is the Higgs, and the long layer is the false carrier. Last layer is the matter field. The right-hand side is the dark matter. The 25%. Right now, 25% of our energy budget of the universe is made of dark matter. And there's plenty of evidence of the existence of dark matter. It's only by gravitational interactions. And from cosmology scale to galaxy scale, from equivalent system to non-equivalent system. So the thing is how do they, maybe the dark matter sector has some particle nature. They will talk to the Standard model. One of the leading scenario for a long time is called weakly interacting massive particle is WIM. So here I just show you one example. They talk by Z, and actually there's more realization. And this is miracle because you give roughly 100 GeV dark matter, you can get the right dark matter density predict 25% of the energy budget. And for this search, and there's a complementary search for it, like direct detection, indirect detection, and also Kaleidus. Unfortunately, we don't have positive results of the dark matter search, but it doesn't mean that it's not there. There's two ways to make a dark matter discovery. One is like make your experiment more sensitive and increase the exposure of experiment, so going down. The other way for discovery is like just go horizontal way, and you look at much larger window. So we are talking about more generalized the dark sector, and especially recently people focus on dark sector. So analogous to the Standard model, dark sector can be more rich structure. We know that dark matter is 25% of the universe, and why not is it's more rich, and also is if this is the matter field, you can imagine there's some false carrier like A prime, or some dark scalar or stellar neutrino, etc. So in this talk, I mostly focus on the dark photon case. We are here. Let me just mean that when they talk to each other using the dark photon portal. Let me explain you more detail what's dark photon. So dark photon is like similar to photon as U1 symmetry, and the U1 symmetry can be spontaneous problem, and the dark photon get a mass. So you can introduce some loop heavy formula over here. When you integrate, you get the effective operator. The effective operator is 1 over epsilon times f mu mu prime f mu mu. F mu mu prime is the dark photon. F mu mu is our familiar photon. This is the effective Lagrangian. We can write down. Doesn't validate any symmetry. So this is actually an awkward coordinate to work on the dark photon, because then you should do the feed redefinition and change to another frame. You will get what's really dark photon similar. So we know the photon is like they couple to EM currents has a mass 0. So what's dark photon? Then after you do the feed redefinition, you will know that dark photon also couple to EM currents, just has a small coupling. The small coupling is proportional to E, but it has suppression on the epsilon, and they have a mass over here. This means that how do we search for them? Every time you have photon produced, you will have a dark photon, and unless there's a kinetic reason to forbid it. So how do we search in the Collider? We know that in the CMS we can search for dark matter using missing energy search. Here we are talking about LCB. LCB is like a forward detector. Here's the collision point. Here all detectors over here. If particles travel this way, you will see it. They design this way for specific purpose. Then on the other side, you normally don't have measurement, so you cannot measure missing. Normally you cannot measure missing ET. So how do we use LCB search for dark matter, dark sector? The thing is like we can use the Velo detector. The Velo detector is near the collision point. So what the Velo detector looks like? We have the proton collision, and here's the interaction point over here. And after the beam stable, and you move the detector as close as possible. The closest point is like, roughly speaking, this is the 6 millimeter away from the collision point. You have the Velo detector. The Velo detector in the transverse direction is like roughly 22 millimeter. I can keep going. So basically, you will see. Oh, okay. So basically, you will see two detectors here. If they electron E plus emerge, you can reach to the track, finally find the point. Either it's displaced or it's from the prompt search. So it's fine. I think this works. Just as I told you, the dark photon has it's same as photon, has small coupling and has mass. It's boiled down this speaking map. So this is coupling versus the mass. Here the plot is not quite updated, but roughly give you the feeling is like the gray region is excluded. You have collider, you have beam dump, you have supernova. Then the white region is our future target. We want to search for them. The question is how LCB search for them. Why it works? The reason is like LC. One reason is like they can go down in this region because LC is really the most advanced detector. So they have high luminosity. They can move this direction. They have a large production rate. And why they can go this way? The beam dump experiment usually is a long displaced vortex. As I told you, the LCB has a much shorter space vortex, so they have small displaced distance, so they can move shorter lifetime and they can probe this region. In principle, LCB has a good chance to cover this region. Then we need to find really promising channel. The promising channel we find is like one meson decay. It's like a Cu bar bound state D0. And when you have Cu bar bound state, you have excited state. Excited state decays to ground state, you emit the photon. And how do we, why this is a promising channel? Because they have less background. Let me explain to you. They have proton collision. Here's a collision point over here. You find the pi plus pi minus or k plus k minus, then you do the invariant mass reconstruction, you find the D0. At a nearby point, in the nearby point, you find the E plus E minus. And when you sum over the four of them, three of them, you get D0 star. So there are two. One is mass constraint geometry, saying you can hear a lot of background. Definitely they have reducible background from the standard model D0 star decay, but this is seems controllable. And one easy step is like is think about display D0 display A prime, and then you can move to the displayed region. You can do the search. So here I show you the 2D map again, and I put a lot of color line. Here's the because there's future search on this. So what the LCB looks like is like they can wipe out the white region and in the future. So they're different shape because one is resonance, the other is displaced. Okay, so I have told you this region is roughly from the two electron mass and goes to 0.2 GeV, and because of the mass difference of D0 star and D0. And how about to go to like larger than that? Then we open the primary space. This is the primary space looks like, and there's a big white region over here. Why this is hard? The region is hard because the mass of that photon is heavy, and one is heavy, then production rate is low. But the boost is smaller. When the mass is larger, then you compute the boost is smaller. So the displace will be much smaller. And we found a very promising meson decay channel. Can we find another meson decay to dark photon in this region? Unfortunately, this region is mostly coming from germanium and a little bit hard. So the idea is like, can we combine all the channels, make the rate as high as possible? The channel we can see is like they just to go back a little bit back. It's like the channel is coming from West Channel and also like QQ bar goes to A prime, offshore A prime, onshore A prime go decay QB plus E minus. They also can come from meson decay pi 0 and either all is producing A primes. The challenging is what's the signal rate? If you don't, let's say I want to combine a channel, if we don't know the signal rate, means that you cannot have any prediction unless you have discovery. It's fine. Before you want to put a bound on the, if you want to know put a bound or put the bound on the map, it's pretty hard. This is the background is covered. Then if you don't know the signal rate height, then you don't know which kind of coupling you are constrained. So let's go back to the dark photon production. When I said that every time you have photon production, you also have the dark photon produced. So here's the signal looks like. The proton generates a bunch of stuff, and the A prime decay to mu plus mu minus. So if the background, that's only from the EM process. It's proton producing the something, and this is offshore dark photon goes to mu plus mu minus. It looks quite the same. And we measure the background. Can be just using the background to predict what's the signal rate. So let's compute the ratio. The ratio signal divided by background, when we compute it at the tree level, they actually proportional to each other. All is boiled down this formula. It's epsilon is the coupling, as I mentioned. Mass is given, and then this is decay rate of A prime. If you give me the two number, you can just calculate the decay rate. This is using the narrow List approximation, and the beam width is given by experiment. So beam width is better, then you get better constraints or reach. So the measured diameter spectrum is the background, EM background. This is not trivial, but after some simulation, choose a proper card. If the background is coming from EM, then you can always use this formula to predict what's the signal rate. This formula is quite general and can be applied to not only applies to LCB or CMS or some pair 2. So LCB measures the dimuon spectrum, and this region is like the other background, like same sign dimuon. So there you see the bump over here is a bump just coming from some mesons. Okay, so go back to the 2D plot, and you don't want to search for the resonance on top of resonance, so we mask this region. And if it's 15 inverse bandbar, here's the dimuon which we will get from LCB. There was a island here because it's LCB dimuon display search. So what's the result for LCB? And they took our method and applied to the 2016 data. Here's the constraint again. You will see there's island. This means that the displacer vortex 2 can do works in the future. This limit will increase. So how the future looks like after you go 15 inverse bandbar as I show you, and this is just 15 inverse bandbar, and in the future maybe high Lumi LC will get 300 inverse bandbar. And there's a gap over here. This is coming from other meson decay like E that goes to A prime, and this can be covered in the future. As I said, the method is general. And if you give me the spectrum, this is coming from background, EM background, you can predict the signal. Then CMS, you can apply this method to CMS. Here is, I think today or yesterday, they put this paper in the archive. And this is CMS constraints for dark photon, and here is roughly larger than 10 GeV to 200. And the red line is LCB, and this curve is coming from the scouting data of CMS. Means that they trigger the dimuon, but just save partial information on dimuon. They cannot reconstruct the whole events. So here, there's another it's a experiment. It's phasor. It's already we're going to construct near the Atlas detector. Then it's like you have dark photon produced in this way, and this is roughly along the beam line, and then you can put the detector here. You can see here's the phasor future reach from phasor and the phasor 2, and this is roughly covered. This will move the pin down constraint up. The next question we want to address is how to go beyond dark photon. Why dark photon is like you can have lepton physics, you can have photon phobic. Then you can put the general coupling, put the coupling more general. Let's say FF bar is fermion coupled to X mu is some U1 boson, and how it works. So basic idea is just translate the previous plot to the new one. There was I'm not going to detail the plot. There's a lot of color coding for different kinds of experiments. So for example, U1 beam SAL. So basically there are three things you need to translate. One is the production rate. After you change your coupling, your production rate will be rescaled. The other is like the decay rate. You produce the A prime, your X, particle X, they will decay to dimuon, then the decay rate will be changed. The third one is the let's say you have efficiency. The efficiency also change, especially for some beam dump experiment. So you can do this conversion, and you can apply the previous dark photon constraints to the new, like U1 beam SL, or U1 only coupled to bion, or U1 proton phobic session. Let me summarize here. So I'm talking about dark photon search at LCB and in detail, and there are two kinds of search proposed. One is like excited meson decay to the ground state, produce the photon or dark photon. The other is inclusive, you sum over all the background. And then I mentioned you can go beyond dark photon, easily map the previous result to the model or the new models. Okay, I will completely switch here, talking about dark photon, dark matter. Before I'm talking about MeV, GeV, dark matter, dark photon. Right now I'm talking about like 10 to the minus 22 eV. So as I said, this is our mentioned production in the early universe, talking about small security issue in the galaxy, and also possible detection in the stars, the sun. So let me set up a stage. Just to remind you, this is light dark photon mass 10 to minus 22 eV to eV, and then it's becoming cosmology stable. And you can think that A prime cannot decay to die electron, and they possibly decay to 3 photons, and you can. This is suppressed by the electron mass of the A prime divided by the electron mass by to the 8th power, I think. Then you have loop suppression of electron, and most basically even for EV, this is stable in cosmology time scale. The other is the W wavelength. And the W wavelength, for example, for 10 to the minus 22 eV, in the galaxy scale, dark matter or dark photon has the W wavelength like kiloparsec. When you choose the mass, this value, and then choose the typical velocity 10 to the minus 3, and this is the scale. So this will change the galaxy scale physics. The last thing that's different from the normal particle, dark matter particle, is the large occupation number. Occupation number, we know that when you integrate the momentum space, you will get a number density. So here, the number density, roughly estimation, is the number density of the A prime divided by the momentum into the cube, ma times b0 cube, you will get 10 to the 76. 76, here's the mass I choose, velocity I choose. So quite different over here. And how do you produce them? Usually when we talk about wind, why is it attractive is because they have thermal production. It doesn't depend on initial condition. Unfortunately, dark photon or axions have to, depending on initial condition, how do you set it? The normal thermal freezing doesn't work. They produce to not dark photon, dark matter, possibly producing relative, more like dark radiation, I guess, radiation, and they cannot be the dark matter. And there's in 2015 there was also suggestion coming from the dark photon coming from inflation quantum fluctuation. It's because this is also scalar field. It's slightly different from the normal scalar, but for the spin one, you still can have quantum fluctuation. Finally, end up some radical abundance in the universe. This year, Lian Tao and his collaborator Andrew Long has an interesting paper using the cosmic string. It's a roughly global cosmic string, and because you take the coupling almost zero, you get the cosmic string. When they evolve in the universe, you produce a lot of dark photon at the momentum order of the Hubble scale. And there's a full paper coming out in the same day in the archive is talking about if you have a heavy matter particle can decay to the dark photon. And you can see also my paper in 1 year before that, I'm thinking about the dark photon is massless. They have more interesting thought that put the dark photon massive, and you can make the dark photon as dark matter. So the basic idea is, as I told you, that maybe axion will not decay to the photon, because photon have thermal mass, even thermal mass is pretty small in today, and the Hubble expansion can just make them stable. So we know that they cannot the wave decay, but when they oscillate in the universe, they have a non-potable thing. It's because the A prime or A get a tectonic mass. The basic idea is like similar to the preheating, and if you have QCD axion, they can predominantly produce a lot of A prime. If there's no dark electron make the plasma mass for the A prime, then this can be the dark matter as a dark matter candidate. So right now we're talking about galaxy scale. We know like cold dark matter is very successful in the cosmic scale, but in the galaxy scale, there's the prediction sometimes different from what we observe. And basically, there's several issues here called Casper core problem, missing satellite, and too big to fail. And the Casper core is very easy. When you look at the dwarf galaxy or this galaxy, you find that the prediction is more like Casper, like NFW profile. But you observe the informed velocity is like core profile. And this is also missing satellite problem is like you predict from simulation like thousands of satellites, but we observe like roughly 10. And too big to fail is focusing the 10 satellites, and there's also discrepancy between simulation and the observation. There's also diversity problem, etc. How do we solve that? there are two dark matter sources. There are several, some dark matter. Here I mentioned two. One is self-interaction dark matter. They just thermalize so in the center, they just thermalize the system and make then the cusp thing will be core. When they thermalize, then you solve the system with gravity, you will find that this is more thermalized system. And the mass of the dark matter roughly 1 GeV, or if you, yeah. For the fuzzy dark matter, there's another way. Why I talked about 10 to the minus 22 eV, I told you the Broglie wavelength is like a kiloparsec. So inside the Broglie wavelength is a core profile, and there's some tension with the lambda alpha measurement, depending on which group you ask. It's maybe the central value will change a little bit. So why is GeV? Why is 10 to the minus 22 eV? And how about something else? How about some different mass? The same is like if we have dark photon. If I have dark photon, they also can be thermalized. As I said, the thermalization can be different from normal things, like because any interaction can thermalize dark matter or thermalize other things. The model I choose is like you have dark electron and dark photon, and they are both stable and become dark matter candidate. At the same time, one is 10%, the other is 90%, or one is or 1% or 99%, depending on the model you like. Then we compute the thermalization rate. The normal particle collision gets the thermalization rate in roughly like n times sigma v. But here we, as I mentioned, like you have large occupation number enhancement. The enhancement can completely change the game, like 10 to the 78. You will make the cross section roughly the same as the self-interaction dark matter. But that's the way to enhance the cross section. There's when we're talking about Bose enhancement, it's like you scattering your final state is already occupied. You get a Bose enhancement. But for this hierarchy structure, you get some cancellations. The cancellation coming from when you calculate the Boltzmann equation, you find that there's a backward and forward scattering. They do cancellation. The cancellation is suppressed by the lighter dark matter mass divided by the heavy one. And when we talk about heavy dark matter, the dark electron, they get a random walk suppression, just like you apply the ping pong ball with bowling ball, and the ping pong ball get the order one momentum change, but the bowling ball just change the momentum a little bit. So you get a random walk suppression. The suppression is just ma prime divided by m psi squared. So here's the result. The ma, the dark photon mass we're thinking about is in the range of the 10 to the minus 22 eV to roughly eV, and here the coupling is not the mixing angle. This is just G prime. This is the coupling between the dark matter, dark electron, and A prime. So when you choose like let's say when you choose your A prime dominant, then you get this line, and when you choose your psi dominant, because you have random walk suppression, you get another line. You need a larger coupling. That's the idea for we call it co-interacting dark matter. Let me mention the last work is about how to detect them. There are many proposals how to detect them. Here we just think like one simple one. Like we know that there's interaction like f mu mu prime times f mu mu. So it means that when the dark photon travel, they will convert to photon. So when they convert, so it means that they will always convert, but the convert rate is pretty small. The rate becoming much larger when the photon gets thermal plasma mass. So the dark photon mass, when the dark photon mass equal to the plasma mass of a photon, they have resonant conversion. And we want to increase we want to find a place has a plasma mass, and we find a place. We also need to find a place has a near us, so like we can increase the flux. One of the we think is like look at the sun, and dark photon traveling and go to the sun and then convert to photon. So the dark photon has we know the sun has a very hot in the center. Sorry, it's like they have large electron density in the center, and then in the infinity is zero, so it's extrapolation. So when dark photon travel, they will just find the sweet spot and convert to photon. And this is the, then finally they become a photon, and then just normal bump hunting structure, you will find the, you can look for the photon using the future experiment like SKA. Here's some preliminary result, and here's the region we are thinking about, and all the other lines is the current constraints, and this blue region is the future solar radial reach. Okay, let me conclude. So I talked about the dark photon search at speed, and also talking about maximum decay and inclusive search. And in the future, we possibly can generate more like to the more hidden, more rich hidden sector model of that FCP or CMS can search for them. The other thing, the second part of talk, I'm talking about dark photon, dark matter, and mention like for the not for 10 to the minus 22, if you're talking about this mass range, you can still solve the small structure issue by introducing the two component dark matter. One is the dark electron, the other is dark photon. And I show some preliminary results on how to detect the dark photon from the sun. That's it.
We have time for questions.
Is your dark photon dark matter is thermal with some temperature?
No, it's not thermal. If it's thermal, then it's in the galaxy. It's obey the Maxwell. It's obey the Maxwell distribution, but it's not definitely not thermal. If thermal cannot be dark matter. But you possibly worry about the one have dark electron and then they have strong interaction. They will thermalize the dark photon. This is the constraint we need to consider. We don't want it becoming thermal.
I was thinking, usually we have 10 to minus 22 eV photon.
Use the microphone.
Yes.
So press the button.
Just press.
Usually, we think of the 10 to the minus 22 eV condensate.
Yes.
Yeah, but now you're a vector field, so I just wonder.
Are they different?
Yes.
Yeah, it's for non-relative scale. They have only the difference is one is have 3 degrees freedom, the other is have 1 within sugar. But when you take the non-relative limit, they roughly behave the same. You can see that. And also the dark photon different from epsilon is like they are calculated much smaller. Usually you have the movie effect. If you want to make dark photon set interaction rate is much smaller than epsilon. The other should be, I think, should follow the same property. Yes.
So because you are assuming very light dark photon field, somehow we have to assume some extra sector to generate the gauge mass.
Yeah, you
like a Higgs mechanism
or Stuffer mechanism. Yeah, or you make
all those kind of extra sector don't affect the physics that those extra sector to generate the dark photon gauge photon mass. They don't affect the physics that you're discussing. Is it a kind of natural assumption, or?
Is it a natural assumption? I didn't see why you cannot make it so light, unless you're talking about a big word conjecture, right?
A simple, as a simple statistical mechanism.
Yeah.
That's what in your mind.
Yeah, it works.
So you can have any kind of string-like object, for instance, with very light tension, or
this I don't know.
There is another interesting opportunity, possibility to look for light particles. Namely, when you have mass small, so the photon length of these particles comparable with the black hole radius, and black hole is rotating, there is effect of superradiance amplification.
Yes.
And it works for every particle, so axions as well, but it will show that for vector particles, this mechanics, because of spin-spin interaction, much more efficient, 2,500 approximately more efficient than axions. So for this reason, for some values of the wavelengths, you can find out instabilities if they exist, and it is also a nice test.
Okay. Cool. So you're talking about super radiance, right?
So,
You're talking about the super radiance function.
yeah.
I think people already have some work.
Yeah, it was a lot of work on this. It's instability of black hole and rotating black hole because of this mechanism.
Sure.
Hi, just a quick question. For the inclusive search part at LHCb, the dimuon background is actually, the dimuon background coming from the offshore standard model photon. It's just the background only for the prompt case, right?
Yeah, this is for prompt case. This is for prompt.
Thank you.
The next question.
Why you say if the dark photon is stable in your cosmology time scale? Because nowadays we don't know yet.
Oh, it's just if I have a model, I compute the decay rate is too small, and you can compute it. It's just the Lagrange level is just the Euler Hesburg operator, like ma prime. It's like roughly the cross section should be ma prime 8 to the m e to the 8th. Then you times loop effect and also the epsilon. Even if it's not stable, you put the epsilon pretty small, it's also stable. You can calculate it this way.
I remember you draw your Feynman diagram. That was on to your one loop and
this one is suppressed because the electron mass is pretty heavy compared to the dark photon mass, so it's stable.
Okay, so let's thank Wei and the previous speaker again.
Outside
so
the phone.
the lunch box is probably outside, then let's come back at
1:30.
1:30.